This is the first video in a series about the sign test. The sign test relies heavily on the binomial test, so I'm going to begin with a review of the binomial test. I call it a review because in the previous video series I discussed the binomial test with some detail, so if you have not watched that series, I recommend you do so. The binomial test is about making an inference for a single proportion. The parameter of interest in this case is pi, the population proportion of success with a Bernoulli event. A Bernoulli event is an event that yields dichotomous data. That is, we will have one of two things happen, either success or failure. In statistics, it does not matter what we define as success. So if we are looking at students passing an exam, we can define success as a pass or as a fail. Obviously, it seems to make a lot more sense to define it in the way we typically think of success as a pass, but statistically, it does not matter. The statistic that we use to estimate the proportion of successes in an observed number of trials is pi hat. Anytime we put a hat on the top of a parameter, we are indicating that we are estimating that parameter from our observed data. In this case, we have n trials, each yielding dichotomous data, success or failure, and x is the number of successes that we observe. So our estimate of the proportion of success in the population is pi hat. Note that this is also our actual success rate in the sample. In order to be able to make inferences, we use the binomial distribution, and the binomial distribution is made up of two parts. The first of these is the probability of one ordering of n joint Bernoulli events with x successes as a function of the probability of success. So in this formula, pi is the probability of success, x is the number of successes, 1 minus pi is the probability of failure, and n minus x is the number of failures. Although we do not know pi when we're making inferences, we can hypothesize it and use that hypothesized value in this formula. Note that when you take pi to the x power, you're simply multiplying pi by itself x times. This is made possible by the rule of joint events when the events are independent. So the formula you see here is only valid if each of our observations are independent of one another. Similarly, 1 minus pi, the probability of failure, is multiplied by itself n minus x times, that is the number of failures. Now when we make inferences, we do not restrict ourselves to one particular ordering of the x successes and n minus x failures. We simply want to know the probability of observing x successes regardless of where these successes fall in the sequence. That is why the binomial coefficient is important. The binomial coefficient is the number of permutations for n Bernoulli events with x successes. That is, if we have n different observations, but they are only of two types, success and failure, how many different ways can we order those? That is given by this equation, n factorial, where n is the number of observations, divided by x factorial, where x is the number of successes, times n minus x factorial, where n minus x is the number of failures. Putting that together gives us a binomial probability. That is, we can calculate the probability of observing x successes in n observations if we know pi, the probability of success, and we're going to hypothesize that, by taking the product of the binomial coefficient and the probability of one particular sequence of events. To create the binomial distribution, we will allow x, the number of successes, to vary from the lowest possible number of 0 up to the highest possible number, the number of observations, n. This then gives us a probability distribution showing all possible outcomes with the probability associated with each outcome, assuming that pi is the probability of success. So now here's how we can conduct the binomial test. Consider n independent Bernoulli trials with the same probability of success, pi, for each trial. The binomial test can test the hypothesis about pi. So we can set a null hypothesis, say pi sub 0, and test it against an alternative hypothesis, which can be one of three types. Either a two-sided hypothesis where we say pi is not equal to pi sub 0, a one-sided hypothesis where the alternative is that pi is greater than this null hypothesized value of pi, or a one-sided alternative in which pi is less than the null hypothesized value of pi. We then construct the binomial distribution with n and our null hypothesized value of pi. We then determine the p-statistic, that is, the prior probability that x is at least inconsistent with the null hypothesis and more consistent with the alternative, given the observed value of x. We reject the null hypothesis if the p-statistic is less than or equal to alpha, our chosen nominal type 1 error rate. Alpha is the tolerance for error. For even more informative inference, we can construct a confidence interval for pi. We do that by conducting hypotheses tests for every possible value of pi sub 0. That is, we set pi to everything between 0 and 1. A 100 times 1 minus alpha % confidence interval is given by all values that result in the retention of the null hypothesis, that is, non-rejection. So in order to obtain a 95% confidence interval, we set alpha, the nominal type 1 error rate, at 5%, test every possible value of pi, and then put all retained values in that confidence interval. If we are doing a one-sided hypothesis test, we'll get a confidence interval that's bounded on one side. If we do two-sided tests, we'll get a confidence interval that is bounded on both sides. Prior to beginning our hypothesis testing, we may want to make sure that we have a large enough sample size, so we can calculate the power of the binomial test based upon our proposed sample size. We determine both the null hypothesis and a specific alternative hypothesis. That is, we cannot just say that the alternative is not the null hypothesis. We have to come up with a specific value. We typically set that alternative hypothesis by choosing the smallest value of pi sub 1 that we still consider an important enough difference from pi sub 0 to warrant this research study. We construct the binomial distribution using n, the number of observations we're proposing, and the null hypothesized value of pi. And then we determine the critical region, that is, all the values of x, the observed number of successes, that would lead to rejection of the null hypothesis. We then construct another binomial distribution, this time using n, our sample size, and the specific alternative hypothesis, and determine the probability of falling in the same critical region that we just calculated using the null hypothesis. That is, we don't calculate a new rejection region, but use the rejection region from the null hypothesis and see what is the probability we would be in that rejection region if the alternative is true. This is the probability of rejecting the null if the alternative is true, and it is called the power of the binomial test. We can create a power curve, such as the one shown here, by trying a variety of different sample sizes and determining what the power would be. A typical standard that is used in our industries, that is in the behavioral, social, and medical sciences, is to have power of at least 0.8 or 80%. So we would want to make sure that we have a sample size that yields at least this much power, with even higher power levels being even more desirable.